Hey everyone, welcome back. Today we're diving into something that sits at the very heart of mathematics and computer science, logic. Specifically, we're going to talk about propositions, connectives, and interpretations. By the end of this video, you'll have a solid intuition for how logical reasoning actually works, not just the symbols, but the meaning behind them. Let's get into it. So, first things first, what even is a proposition? A proposition is simply a declarative sentence, one that makes a claim. And the key rule is it must be strictly either true or false. Never both, never neither. Let's look at some real-life examples. Take the sentence, "It is raining right now." That's a proposition. You might not know the answer right now, but it's definitely one or the other. Either it is raining or it isn't. So, proposition. Now, Paris is the capital of France, also a proposition. And this one we can evaluate. It's true. But what time is it? That's a question. Questions don't make a claim, so they can't be true or false, not a proposition. Mathematically, 2 plus 2 equals 4, true, proposition. 10 is less than 5, false, but still a proposition. Here's the tricky one. X plus 5 equals 10. Is this a proposition? No, because the truth value depends on what x is. Without knowing x, we simply can't say. So it's not a proposition. It's what we call an open statement or a predicate. We'll deal with those another day. Now that we know what a proposition is, let's ask, what can we do with one? A unary connective takes a single proposition P and maps it to a truth value. Think of it as a machine. One input goes in, one truth value comes out. Since there are only two possible inputs, true or false, there are exactly 2 squared, that is, 4 possible unary functions. Let's list them all. F1 always outputs true, no matter what. We call this a tautology, like saying the sun exists. It's always true regardless of anything else. F2 just echoes back whatever you put in. Input true, get true. Input false, get false. That's the identity. It changes nothing. F4 always outputs false, no matter what. That's a contradiction, something that can never be true, like saying I exist and I do not exist at the same time. And then there's F3, negation. This is the one that actually does something interesting. And because it's so important, let's zoom in on it. Negation, written as this symbol, not P, is beautifully simple. It just flips the truth value. If P is true, not P is false. If P is false, not P is true. Let's make it concrete. Say P is the statement, the TV is on. Then not P is, the TV is not on. Now, if the TV really is on, and I say the TV is not on, I'm lying. That's false. But if the TV really is off, and I say the TV is not on, I'm telling the absolute truth. That's true. Simple, right? Negation is your logical way of saying the opposite of that. Keep this in your toolkit. You'll use it constantly. All right, now let's level up. What if we have 2 propositions, P and Q, and we want to combine them? That's where binary connectives come in. A binary connective takes 2 propositions and outputs a single truth value. Now with 2 inputs, we have 4 possible input combinations, both true, P true, Q false, P false, Q true, and both false. Each of those 4 slots can independently be true or false, giving us 2 to the power of 4. That's 16 possible binary functions. In the next slide, we'll lay out all 16, but don't worry, we won't torture you with all of them. We'll focus on the ones that actually matter, the ones that power human reasoning and every computer ever built. Here they are, all 16 binary connectives laid out in one massive truth table. Each column represents a different function, numbered 0 through 15. Now, most of these are either trivial or redundant, so let's quickly categorize them. Functions 0 and 15 are constants. One always outputs false, the other always true. These are your contradictions and tautologies. Functions 3, 5, 10, and 12 just spit back a single variable, P, Q, or their negations. Not very interesting. But the rest, these are the ones that matter. Function 8 is AND. Function 14 is OR. Function 6 is XOR, exclusive OR. Function 9 is XNOR, also called the biconditional. Function 1 is NOR, function 7 is NAND, and functions 13 and 11 are the two forms of implication. We're now going to deep dive into each of the important ones. Get your newts ready. First up, conjunction, or AND, written as P wedged Q. The rule is strict. AND is only true when both P and Q are true. If even one of them is false, the whole thing is false. Here's a great way to remember it. Imagine a parent making a promise to a child. I will buy you ice cream and a toy. Now, did the parent keep that promise? If they buy the ice cream and the toy, yes, promise kept, true. If they buy the ice cream but skip the toy, nope, promise broken, false. If they skip the ice cream but buy the toy, still broken, false. And if they buy neither, completely broken, false. AND is an all-or-nothing deal. Both conditions must be satisfied. Next up, disjunction, or inclusive OR, written as P violentium Q. This one is much more generous. OR is true as long as at least one of the propositions is true, including the case where both are true. Think of a job posting that says you must have a math degree or a physics degree. If you have both, you're hired, true. Only a math degree, hired, true. Only a physics degree, still hired, true. Neither degree, sorry, you're not getting the job, false. The only time OR fails is when both inputs are false. That's the key distinction, and it's what separates inclusive OR from exclusive OR, which we'll see next. Now this is a fun one, XOR, or exclusive OR, written as P XOR Q. XOR is true when exactly one of the inputs is true. If both are true or both are false, it returns false. Think of a restaurant that says your meal comes with soup XOR salad. If you try to grab both, the waiter stops you. That's false. Take only the soup, perfectly fine, true. Take only the salad, also fine, true. Refuse both? Well, you didn't make a valid choice from the offer, false. XOR shows up everywhere in computer science. It's a fundamental operation in cryptography, binary arithmetic, and error detection, so remember it well. Okay, here's the one that trips people up the most, implication, written as P arrow Q, read as if P, then Q. The rule is implication is false in only one case, when P is true and Q is false. In every other case, it's true. Let's use an example. A parent tells their child, if you get an A, then I will buy you a car. You get an A, and they buy you a car. They kept their word. True. You get an A, but they don't buy you the car. They lied to you. That's the only false case. Now here's where it gets interesting. What if you don't get an A? No A, but they buy you a car anyway. They were just being generous. They technically never lied, because their promise was specifically about the A. True. No A and no car? Well, the condition was never triggered, so they didn't lie either. True. This is called vacuous truth. When the premise is false, the implication is automatically satisfied. It feels weird, but it's logically consistent. The only way to break a promise is to fulfill your end and then not follow through. Last major connective, the biconditional, written as P left-right arrow Q, and read as P if and only if Q. This one is true when both propositions have the same truth value, both true or both false. Example, we will play the match if and only if the weather is sunny. Both play and sunny, rule followed, true. Play but it's raining, rule broken, false. No match but it's sunny, rule broken, false. No match and it's raining, rule followed, true. The condition was not met and neither was the outcome. Both sides matched. The biconditional is essentially an equality check for truth values. You'll also see it written as XNOR in digital circuits because it's the exact opposite of XOR. And that brings us to our cheat sheet. Everything in one clean table. Let's go over the quick rules one final time so they stick. And, only true when both are true. One bad apple spoils the whole thing. Or, only false when both are false. Be generous, accept anything. Implication, only false when true leads to false. A truth cannot logically produce a lie. If and only if, true when they match, both true or both false. These 5 connectives, not, and, or, implication, and biconditional, are the building blocks of all mathematical logic. Every theorem, every proof, every program, every circuit. At some level, it all comes back to these. That's it for today. If you found this helpful, hit that like button and subscribe for more. In the next video, we'll start building compound propositions and evaluating complex logical expressions. See you then!